Okay, everybody. Welcome to your next video installment of learning. What we're going to talk about now are products of vectors. So, we've got two types. Okay, we can have a scalar, or we can have a vector product. Okay, now let's talk about scalar first. So, scalar product, say we've got vector A and vector B. Okay, scalar product is also called the dot product because of the notation. So, vector A dot vector B, dot product. Okay, so how this works, say we've got our two vectors. Let's go with vector A and vector B. You're going to draw them with their tails at the same point. So here's vector A and here's vector B. Okay, and you've got some angle in between, call this phi, an angle in between. Okay, AB, or the dot product of A and B, is defined as the magnitude, magnitude of vector A multiplied, so times, the component of B parallel to A. So the component of B parallel to A would be this component right here. Okay? So that component is B cosine of phi. So in other words, the dot product of AB is the magnitude of A, or just A, times B cosine of phi. Okay? Now, when do we actually use this? Well, work is actually defined as the dot product of force times the displacement. Okay? Now, just a quick little tidbit of information. The scalar product of two perpendicular vertices is 0, always, which makes sense. If we had vector A times vector B, well, it would be the magnitude of A times the unit of B parallel to A. Well, there isn't one. It's 0. So, this is a really helpful tool to help find the angle in between vectors when you know the components. Now, you could also have this vector A dot vector B as the sum of their components, the products of their components. Oops. Here we go. AY, BY. You could also have it like that. So to go forward, we should really review unit vectors. Okay, and what those are. So unit vectors are just a convenient way of notation for expressions with vectors involving their components. Okay, so for an XY coordinate system, okay, you have a little I hat, lowercase I with a hat on it, and that is indicative of the positive x-axis. That's where that unit vector points. Okay. You also have, not used to lion yet. You also have a j hat, lowercase j hat, and that indicates or that points in the positive y-axis. Okay, so if we had a coordinate system over here, you would have I right here, and you would have J right here. Now these are completely unitless with a magnitude of 1. Alright? So, a vector A, let's go with vector A, can be defined as AXI plus AYJ. Okay? B, same thing. BXI plus BYJ. Now, if we are working in 3 dimensions, so we have a z-axis, then we have a third letter, k hat, and it points in the positive z-axis. Z-axis. Okay? So, how do we actually use these? Well, give you an example. Give you 2 vectors. You got vector D, and it is defined as 6I plus 3J minus K meters. And we've got vector E, and it is defined as 4I minus 5J plus 8K meters. And let's say they want us to find 2D minus E. Okay, so how we can do that is, let's say that gives us some vector F, magnitude of F. So F, vector F, is defined as 2 times, we got our vector D here, so 6I plus 3J minus K meters, and then minus 4I minus 5J plus 8K meters. Okay, so what we're going to do, distribute the 2, and we're going to combine like terms. So all of our I hats, we're going to group them, all of our J hats, and all of our K hats. So F equals, let's go 12 minus 4 I plus 6 plus 5J, and then plus negative 2 minus 8K. And all of that is still in meters. So F is given as 8I plus 6 plus 5 gives us 11, and then minus 10K meters. So to actually find the magnitude of this, well, the magnitude of F is given as F equals, we've got the square root of Fx squared plus Fy squared plus Fz squared, using the Pythagorean theorem. Well, Fx is just 8, Fy is just 11, and Fz is negative 10. So plugging all that in, you get a displacement of 17 meters. So that's a little bit of use of unit vectors. Now, let's move on. Let's go to, hang on, if I can get my program to cooperate. Here we go. Okay, so let's use unit vectors, and we'll find an angle between 2 vectors with known components. So let's say we've got 2 vectors, vector A, and it is 2i hat plus 3j hat plus k. And we've got another vector, vector b, and it is negative 4i hat plus 2j minus k. Okay. And we want to find the angle between these two vectors. So if we remember, our dot product was given as the sum of the products of our components. Okay? So if we do that, using our components up here, we get 2 times negative 4 plus 3 times 2 plus 1 times negative 1. So our dot product, our magnitude, it comes out to be negative 3. Now if we remember also, our magnitude of our dot product also equaled AB cosine of phi, or the angle between the two vectors. Okay, well, what's the magnitude of A and what's the magnitude of B? Well, we can use the Pythagorean theorem again. Oops, not bx squared, excuse me, ay squared plus az squared. And then for magnitude of B, we've got bx squared plus by squared plus bz squared. So plugging in our components here, we get a magnitude of A as the square root of 14, and we get a magnitude of B as the square root of 21. So plugging those back in, we know that the magnitude equals negative 3. Now we know the magnitude of A and the magnitude of B, 21. So now we can solve for phi. And if you do that, you would end up with phi as equaling 100 degrees. So that's a handy way of using scalar products to figure out angles in between vertices.